Hello students, I am Dr. Sangeeta Sharma, your science teacher. Today we will be continuing with chapter 10 of your science book, that is light, reflection and refraction. In today's video, that is part 9, in text exercises, we are going to solve all the exercises given in between the chapter related to refraction of light. Students, we have learnt what refraction of light is and we have seen the image formed by concave lenses and convex lenses. We have learnt about the lens formula, the linear magnification produced and the power of the lens too. And we have learnt how the sign conventions are going to be used for numerical problems. So let's recall all the formulae used for refraction of light and then we will solve all the problems given. So the first formula used is the lens formula. The lens formula is 1 upon f is equal to 1 upon v minus 1 upon u. Students, here f is focal length of the lens, v is the distance of the image from the lens and all the distances have to be measured from the optical center. Then u is the distance of the object from the lens. Students, mind this that here we have a negative sign and in case of spherical mirrors we had a positive sign over here. The next formula used here will be related to the magnification and the magnification formula is given by the ratio of size of the image to the size of the object, which can be denoted as h2 upon h1, which is also equal to v upon u. Here h2 is the height of the image, h1 is the height of the object, v is the distance of the image from the lens and u is the distance of the object from the lens. The third formula used is related to power of the lens, which is given by the reciprocal of focal length and here the focal length has to be in meters. And the SI unit for power will be in meter inverse or you can say diopter, which is denoted by capital D. There is one more formula used, that is of refractive index. We denoted it by mu and in some books you will find it denoted by small n. So it can be denoted by small n also, and the refractive index is given by the speed of light in air or vacuum upon the speed of light in the medium. So these will be the four formulae used for refraction of light. So we will be going to use these formulae and let's solve all the exercises given in between the chapter. To begin with the first problem. A ray of light travelling in air enters obliquely into water. Does the light ray bend towards the normal or away from the normal? Why? यहाँ पर स्टूडेंट्स हमें ये बताना है कि अगर एक रे ऑफ लाइट ओब्लिकली एंटर करती है वाटर के अंदर तो लाइट रे जो है वो एयर से वाटर में एंटर कर रही है, यानी कि मीडियम चेंज हो रहा है. तो जब मीडियम चेंज हो रहा है तो हमें ये बताना है कि लाइट रे जो है वो नॉर्मल की तरफ बेंड होगी या नॉर्मल से दूर बेंड होगी. So students, we recall that we have learnt that whenever the medium changes, the light ray changes its path. Otherwise, it would have moved in a straight line. So when the medium changes, the light ray changes its path because the speed of light changes. That is, the speed of light is different in different mediums. Now here we have two mediums, air and water. Now since the refractive index of air is 1.003 and the refractive index of water is 1.33. This is the refractive index of air and this is the refractive index of water. What we see is that the optical density of air is less as its refractive index is less and the optical density of water is more. So what we observe here is that the light ray is entering from a rare medium to a dense medium. So whenever light ray travels from a rare medium to a dense medium, it bends towards the normal because the light ray changes its speed and the speed decreases in the denser medium. So this is what we have written as the answer. The light ray bends towards the normal. When a ray of light travels from a rare medium to a dense medium, it bends towards the normal. Since water is optically denser than air, therefore the light ray travelling from air into water will bend towards the normal as the speed of light decreases in water. This we have shown with a figure. So what we have shown here is that the rarer medium, which is air, and the denser medium, which is water. So the incident ray of light, which is incident at this point, and this yellow line shows the interface where the two mediums are meeting. So when the incident ray of light is incident at some angle, say I, which is the angle between the incident ray of light and the normal drawn at the point of incidence, then what we see is that if the medium was not changing, then the light ray would have moved in this straight line. But since the medium is changing, so the light ray changes its path. Light ray यहाँ से आ रही थी स्टूडेंट्स और इस डायरेक्शन में जाती अगर मीडियम चेंज नहीं होता, पर मीडियम के चेंज होने के कारण लाइट रे बेंड कर जाती है और रिफ्रैक्टेड रे जो है वो इस डायरेक्शन में मिलता है इन प्लेस ऑफ दिस डायरेक्शन. तो यहाँ पर स्टूडेंट्स हमने क्या देखा, दैट द लाइट रे हैज बेंट टुवर्ड्स द नॉर्मल. लेट्स सी द नेक्स्ट क्वेश्चन. Light enters from air to glass having refractive index 1.50. What is the speed of light in the glass? The speed of light in vacuum is 3 into 10 to the power 8 meters per second. So students, here we are given the refractive index of glass, that is 1.50. This is the symbol for refractive index. In some books you might find n, small n. So we can write n or we can write mu. So the refractive index is given as 1.50 and the speed of light, which is denoted by C, the speed of light in air or we can say vacuum, which is denoted by C, is given by 3 into 10 to the power 8 meters per second. Now what we need to find? We need to find the speed of light in the glass, that is we need to find V. Now students, here the formula used is mu is equal to speed of light in vacuum upon speed of light in the medium, which is given by C upon V. So what we see here students is that if I substitute the values, then mu is 1.5, speed of light in vacuum is 3 into 10 to the power 8 and we need to calculate V. So what we see here students is that V is 3 into 10 to the power 8 upon 1.5. So we can cut this and we get the speed of light as 2 into 10 to the power 8 meters per second. So we have calculated the speed of light in the medium, which is given to be glass. V comes out to be 2 into 10 to the power 8 meters per second. Let's see the next problem. Find out from table 10.3, this is the table given, the medium having highest optical density, also find the medium with lowest optical density. This is the table. Now students, here in this table we are given the material mediums, the names of the material mediums and their refractive indices. So what we see here is that the refractive indices are arranged in an increasing order. What we see here is that the refractive indexes are arranged in an increasing order And as we know students that the refractive index gives us an idea about the optical density. If the refractive index is small, then the optical density is less, and if the refractive index is large, then the optical density is also large. So what we see here is that air is having the lowest refractive index, that is 1.003. So air is going to be having the lowest optical density, and then what we see is that diamond is having the highest refractive index. So it will have the highest optical density, or you can say the largest optical density among the material mediums which are given in this table. So the answer will be given as that the medium with highest optical density is diamond and the medium with lowest optical density is air. Let's see the next problem. You are given kerosene, turpentine and water. In which of these does the light travel fastest? Use the information given in table 10.3. This is again the table, the same table 10.3. And what we need to find here is, first we can observe the three things, the three material mediums. Kerosene, the refractive index is 1.44. Turpentine, the refractive index is 1.47, and water. So these are the three material mediums given, and what we need to find is that in which of these does the light travel fastest. Now students, we have the formula mu is equal to C upon V, where C is the speed of light, and again the speed of light in air or vacuum is a constant given by 3 into 10 to the power 8 meters per second. So what we observe from this formula is that the refractive index is inversely proportional to the velocity. The refractive index is inversely proportional to the speed of light in a medium. So here what we see is that if the speed of light in a medium is going to be large, the refractive index is small, or what we can say is that for the material mediums having small refractive indices, the speed of light is going to be large, and for large refractive indices the speed of light is going to be less. इन्वर्सली प्रोपोर्शनल है ना स्टूडेंट्स, तो इन्वर्सली प्रोपोर्शनल का मतलब क्या होता है कि अगर एक क्वांटिटी बड़ी है तो दूसरी क्वांटिटी जो है वो छोटी होगी. तो अगर रिफ्रैक्टिव इंडेक्स ज़्यादा है तो स्पीड ऑफ लाइट किसी मीडियम के अंदर कम होगी, और अगर रिफ्रैक्टिव इंडेक्स कम है तो स्पीड ऑफ लाइट जो है वो ज़्यादा होगी. तो यहाँ पर हम क्या देख रहे हैं कि रिफ्रैक्टिव इंडेक्स और स्पीड ऑफ लाइट इन अ मीडियम इन्वर्सली प्रोपोर्शनल हैं, और इन तीन के अंदर अगर हम अरेंज करें तो यहाँ पर सबसे कम रिफ्रैक्टिव इंडेक्स किसका है? वाटर का, उसके बाद में केरोसिन और उसके बाद में टर्पेंटाइन ऑयल. यानी यहाँ पे जो सबसे ज्यादा रिफ्रैक्टिव इंडेक्स है वो किसका है? टर्पेंटाइन ऑयल का, और सबसे कम किसका है? वाटर का. यानी वाटर की ऑप्टिकल डेंसिटी सबसे कम है, तो स्पीड ऑफ लाइट यहाँ पर वाटर के केस में सबसे ज़्यादा होगी. और टर्पेंटाइन ऑयल जिसका कि रिफ्रैक्टिव इंडेक्स इन तीनों में सबसे ज़्यादा है, यानी इसकी ऑप्टिकल डेंसिटी सबसे ज़्यादा है, तो स्पीड ऑफ लाइट इसके अंदर सबसे कम होगी इन तीनों के कंपैरिजन में. सो द आंसर विल बी that since mu is equal to speed of light in vacuum upon speed of light in the medium, which is given by C upon V, so mu is inversely proportional to the speed of light in the medium. Hence light will travel the slowest in the material which has the highest refractive index, and travel the fastest in the material which has the lowest refractive index. From the table 10.3, the refractive indices of kerosene, turpentine and water are 1.44, 1.47 and 1.33 respectively. Therefore, light travels the fastest in water. So this is the way how we will write the answer for this problem. Let's see the next question. The refractive index of diamond is 2.42. What is the meaning of this statement? Now students, here we are given the refractive index of diamond, and as we know, the formula is that mu is equal to speed of light in vacuum upon speed of light in the medium, which is denoted by C upon V. So mu, which is given for diamond, is 2.42 and the speed of light in vacuum is 3 into 10 to the power 8 meters per second, and speed of light in the medium we need to calculate. So on rearranging, we will take V here and 2.42 will come here. So V becomes equal to 3 into 10 to the power 8 upon 2.42, which can be solved, and on solving we will get 1.24 into 10 to the power 8 meters per second. So what we see is that the speed of light in the medium, that is diamond, has reduced. So the speed of light in air was 3 into 10 to the power 8 meters per second, and it is reduced by a factor of 2.42. So the answer will be that this implies that the speed of light in diamond will reduce by a factor of 2.42 compared to its speed in air or vacuum. Let's see the next problem. A concave lens has focal length of 15 centimeters. Focal length of 15 centimeters. At what distance should the object from the lens be placed so that it forms an image at 10 centimeter from the lens? Also find the magnification produced by the lens. Now students, here we will begin the solution by writing the quantities which are given. So we will first write the quantities which are given. A concave lens. Students, here we have the concave lens, has a focal length of 15 centimeters. Now since this is a concave lens, thus the focus is in front of the lens, and in order to measure the focal length we have to move in a direction opposite to the direction of incident ray of light. So this focal length will be with a negative sign. So here we will draw, say a concave lens is this, having a principal axis like this, then it is given that the focal length, which is the distance between the optical center and the focus, is given to be 15 centimeters. So F is 15 centimeters. Now since we have to measure all the distances from the optical center, so we need to move in a direction opposite to the direction of incident ray of light. So F is going to be negative. Then at what distance should the object from the lens be placed so that it forms an image at 10 centimeters? Now the image is given to be at 10 centimeters. Now in case of concave lenses, we know that all the images are formed on the left side of the lens. So here again the image is formed in front of the lens, so the image distance will be taken as negative, because in order to measure the distance of the image from the lens, that is from the optical center of the lens, we need again to move in a direction opposite to the direction of the incident ray of light. So here we need to calculate that where the object has to be placed, that is we need to calculate U. Now students, here again we will going to be using the lens formula. So the lens formula is 1 upon F is equal to 1 upon V minus 1 upon U. So here we will solve this. So on using the lens formula, that is 1 upon F is equal to 1 upon V minus 1 upon U, and we need to substitute the values. The focal length was minus 15 centimeters. So 1 upon minus 15, and V was given as minus 10, and we need to calculate the value of U. On rearranging this, I will take 1 upon U on the left hand side and 1 upon 15, the negative of 1 upon 15 on the right hand side. So on rearranging, what we get is 1 upon U is equal to minus 1 upon 10 plus 1 upon 15. Here we will take the LCM, and the LCM can be taken as 30. 10 3s are 30, so this will become minus 3, 15 2s are 30, so this will come out to be plus 2. Again on solving this, I will have minus 1 upon 30, and on reversing, since it is 1 upon U is equal to minus 1 upon 30, U will become equal to minus 30 centimeters. So here the object has to be placed in order that we get an image at 10 centimeters. So this is what was asked, that what distance should the object from the lens be placed so that it forms an image at 10 centimeter from the lens. Also find the magnification produced. So here we need to find the magnification also. Now students, the formula for magnification is V upon U for spherical lenses. So V is given as minus 10 centimeters and U we have found, and it is equal to minus 30. The negative sign will go with the negative sign, and we will be left with 1 upon 3, which can be solved, and this will come out to be say 0.33. Now students, what we observe here is that the value of M is positive. Now positive values of magnification indicates that the image is virtual. All images which are virtual are always erect, and since the value of M is less than 1, so what we get is that the size of the image is diminished, that is the size of the image is smaller than the size of the object. So this is going to be the solution, that U is equal to minus 30 centimeters and the value of M is 0.33, and the inference drawn is that we are going to get a virtual, erect and diminished image. So let's see the next problem. A 2 centimeter tall object is placed perpendicular to the principal axis of a convex lens of focal length 10 centimeters. The distance of the object from the lens is 15 centimeters. Find the nature, position and size of the image. Also find its magnification. Again we will start with writing all the quantities which are given. So first we will write given. We have a convex lens. So a 2 centimeter tall object is placed perpendicular to the principal axis of a convex lens. Now here students, what is given is the height of the object, and the height of the object is 2 centimeters. Now it is taken as positive because the object is placed above the principal axis. What next is given? That the focal length of the convex lens is 10 centimeters. So F is given 10 centimeters. Now students, what we see here is that we have a convex lens, and for convex lenses the focal length is positive because the principal focus lies on the right of the lens. Then what is given? The distance of the object from the lens is 15 centimeters, that is U is given and it is 15 centimeters. Now students, here u is the distance of the object from the lens, and since the object is always placed in front of the lens, that is on the left side of the lens, and in order to measure this distance we have to move in a direction opposite to the direction of incident ray of light. So, u is going to be negative. Then what we need to find? We need to find the nature, and for nature we need to calculate m, the position and size of the image. That is, we need to calculate v, we need to calculate m, and we need to calculate the size of the image. Now, what is given? F is plus 10 centimeters and u is minus 15 centimeters. So, what we will use here is, we will use the lens formula. So, let us begin with the lens formula. Now, the lens formula is 1 upon f is equal to 1 upon v minus 1 upon u. Now, students, here the focal length was plus 10 centimeters and u was minus 15 centimeters. So, the focal length was 10 centimeters and u was minus 15 centimeters. So, on rearranging, what I get is that 1 upon u comes out to be 1 upon 10. This negative sign will go with this negative sign. So, on taking it on the left hand side, we will get again a negative sign. On taking the LCM will again be 30, and what we see here is 10 3s are 30 and 15 2s are 30. So, we will get 1 upon 30. On reversing, v will come out to be 30 centimeters. The positive value of v indicates that the image is formed on the right hand side of the lens. Now, what we next want to calculate? We need to calculate the nature, and to calculate the nature we must calculate the value of m, that is magnification. So, m, which is given by v upon u, v comes out to be 30 and u was minus 15. So, the value of m becomes minus 2. Now, here students, m is negative. Now, what does this negative sign of m indicate? The negative sign indicates that the image is real, and all real images are inverted. And here, since the value is greater than 1, the value of m is greater than 1, it is minus 2, that is, the value of m is greater than 1. So, we are getting a enlarged image. Right students? Now, we need to calculate the size of the image. Again, the formula used is m is equal to h2 upon h1. So, here h2 we need to find and m is minus 2. So, minus 2 is equal to h2 upon h1 was 2 centimeters. So, the height of the image comes out to be minus 4 centimeters. So, here students, we have calculated the value of m, we have calculated the value of v, and we have calculated the value of h2, that is the size of the image. Let us move to the next problem. Define one diopter of power of a lens. Now, students, power of a lens is given by the reciprocal of focal length, where focal length is always taken in meters. So, 1 upon meter gives you the unit for power, that is 1 upon meter is equal to diopter, that is the power of lens is taken as diopter. Now, what is asked here is that define one diopter of power of a lens. So, we will write it like this, that power of a lens is defined by reciprocal of focal length of the lens, that is P is equal to 1 upon F, where F is in meters. So, the SI unit of power of lens is diopter and it is denoted by the letter capital D. So, when F is taken to be 1 meter, then P is equal to 1 upon F is equal to 1 diopter. So the definition will go like this, that 1 diopter is the power of a lens of focal length 1 meter, and 1 diopter is given by 1 meter inverse. Let's see the next problem. A convex lens forms a real and inverted image of a needle at a distance of 50 centimeter from it. Where is the needle placed in front of the convex lens if the image is equal to the size of the object? Also find the power of the lens. Now students, what is given here? That the size of the object and the size of the image is equal. So students, recall that where the object has to be positioned in order to get a equally sized image. Yes, the position of the object has to be on the center of curvature, which is denoted by C1, or in some books we have 2F1. Here we have denoted it always by 2F1. So when an object is placed at the center of curvature 2F1 of a convex lens, its image is formed at the center of curvature 2F2 on the other side of the lens. The image formed is real, inverted and on the same size as the object, and this is shown in this figure, that when the object AB is kept at 2F1, we take 2 rays of light and we see that the image is formed at 2F2. A dash B dash is the image, and what we see here is that the size of the object is equal to the size of the image. Now students, what we need to calculate here is that what is given, that a real and inverted image of a needle at a distance of 50 centimeters. So what is given here? It is given that the image is formed at 50 centimeters from the lens, that is V is given, and what we need to calculate is, we need to calculate U, and as we know that U is the position of the object and the object is also placed at the principal focus. So U will also be 50 centimeters. This we can prove mathematically also. How we will prove it mathematically? That since M is equal to V upon U and the magnification is given as +1, since the size of the object is equal to the size of the image. So what we get is that 1 is equal to V upon U, and this implies that V is equal to U, that is the position of the image and the position of the object is same. So what we get here is that U becomes equal to 50 centimeters. Now students, here if we use the proper sign convention, then what we get is that the image is inverted, right, and all inverted images are real. So what does this indicate? This indicates that the value of M has to be taken as negative, and if the value of M is negative, then V is equal to minus U, that is the value of U is minus 50 centimeters. We can solve this and we can say that U is in front of the lens, so the value of U is going to be negative. We have proved this mathematically also. So we have the value of U as minus 50 centimeters and the value of V as plus 50 centimeters. And what we need to calculate? We need to calculate the power, that is P. And as we know that the power of the lens is 1 upon F, where F has to be in meters. So in order to calculate the power, we need to calculate the focal length. U and V are given and we need to calculate the focal length. So we will use the lens formula. So let's use the lens formula to calculate. So using the lens formula, 1 upon F is equal to 1 upon V minus 1 upon U. And substituting the values with proper sign convention, V was 50 centimeters, this negative sign is by the formula, and the value of U is minus 50. This negative sign will go with this negative sign, so we will have 1 upon 50 plus 1 upon 50. So this will turn out to be 2 upon 50. So, on reversing the values, what we get is that f is equal to 50 upon 2, that is 25 centimeters. Now, students, we have to take the value of f in meters. So, converting this value of f, that is 25 centimeters, into meters, what we need to do is we need to divide it by 100. So, the value of f comes out to be 0.25 meters. Now, we need to calculate the power of the lens. So, P is equal to 1 upon f, where f is in meters. So, we will substitute the value of f in meters. We can remove this decimal, and when the decimal will be removed, we will have 2 zeros in the numerator. So, if we cut it, 25 fours are 100. So, what we get is that the power of the lens is 4 diopters. Right, students? So, we have calculated the power of the lens, and this was asked. Let's move on to the next problem. Find the power of a concave lens of focal length 2 meters. Now, students, here we have a concave lens, and for concave lens, the principal focus is on the left side of the lens. That is, the focal length for a concave lens is negative. What we need to calculate here is, so this is given. So, we can write given. Given is the focal length, and since it is a concave lens, so the value has to be negative. What we need to calculate? We need to calculate the power. The formula used is P is equal to 1 upon f. That is 1 upon minus 2, and on solving this we get a negative sign, and 2 5s are 10 with a decimal point, and the unit is diopter. So, the power of the lens, power of the concave lens becomes 0.5 diopter with a negative sign. In place of diopter, we can write meter inverse also. So, students, today we solved all the in-text exercises, that is all the exercises given in between the chapter related to refraction of light. In tomorrow's video, we will solve all the exercises given at the back of the chapter, that is at the end of the chapter. So, come prepared, recalling, revising all the formulae used. Till then, stay safe, stay healthy. Bye.